Hello, in this video I will be solving problem 6.13 of David J. Griffith's Intro to Electrodynamics, 4th edition. And in problem 6.13 it says, suppose the field inside a large piece of magnetic material is B naught, so that H naught is equal to 1 over mu naught multiplied by B naught minus M, where M is a frozen-in magnetization. Part A of this problem states, now a small spherical cavity is hollowed out of the material. And in figure 6.21 down here, we can see what the sphere looks like. Find the field at the center of the cavity in terms of B naught and M. Also find H at the center of the cavity in terms of H naught and M. Now, simply, we'll first understand what we're given. We're given H naught and B naught. H naught is the H of our original field, and B naught is the field inside our original magnetic material before the cavity is made. Now, simply, to understand what we're doing here, we're removing this sphere from our magnetic material, and the sphere has a magnetic field of itself. So we're just removing the magnetic field of the sphere. And in example 6.1, we find that a sphere's magnetic field is just 2/3 mu naught M. So removing this from our original magnetic material would just be B is equal to B naught minus 2/3 mu naught M. So our new field with this spherical cavity is B naught minus 2/3 mu naught M. Now to find H at the center of the cavity, we can consider H and H naught's relationship. Now given, we see that H naught is equal to 1 over mu naught times B naught minus M, where, as always, H is equal to 1 over mu naught B. So, plugging that in for our H naught, we'll see that H naught is equal to just H minus M, which when rearranged, H is equal to H naught plus M. So now that we have a different field, our H naught has changed. So, first we'll plug in what our original value for H naught was, which is 1 over mu naught times B naught minus M plus the M here. So our new H is 1 over mu naught B naught, which typically for our new space would equal 1 over mu naught times B naught minus 2/3 mu naught M. So, H is equal to 1 over mu naught B minus 2/3 M. Which now, to relate back to H naught, we sub it in. So, H is equal to H naught plus M minus the 2/3 M. So, H is equal to H naught plus 1/3 M. And that's the H at the center of our cavity. Now, part B tells us to do the same for a long needle-shaped cavity running parallel to M, which can be seen here again in figure 6.21, which is just parallel with M. So, essentially a long needle-shaped cavity is just a long solenoid. So, considering what we're removing from our original space, the magnetic field of our removed cavity is just that of a long solenoid. And a long solenoid has a magnetic field of mu naught K. And so our new field would just be simply B is equal to B naught minus mu naught K. However, we want to find it in terms of M as well. So to do this, we'll see our problem references figure 6.21, where our cylinder looks like so. And M points, let's say, in the positive Z hat direction. So that, say, Y runs here, X runs here. And just essentially a long solenoid has these like dimensions. So K would just equal M cross N, and N sticks out in S hat direction. So m z hat cross n hat is equal to m z hat cross s hat, which is just equal to m in the phi hat direction. So our k runs around our solenoid. So b would just equal to, or our k would just equal to mu naught, or just m simply. So of course our total field would just remain the same of b is equal to b naught minus mu naught m. So that's the new field with this cavity removed. Now to find h for this cavity, we're going to consider, of course, the same thing, which is h is equal to 1 over mu naught b for an empty space, which with our new field, h is equal to 1 over mu naught b naught times mu naught m, which when multiplied together, 1 over mu naught b naught minus m is our value for h, which if you realize is equal to our own original h naught. So h is equal to just h naught for this cavity. Now, part C says to do the same again for a thin wafer-shaped cavity perpendicular to m, which we can see here. Now, this one is a little more tricky to understand the concept behind. However, it's again similar to a solenoid, and also sort of a loop, but more crushed. So, of course, similar to a solenoid, our B would just equal to mu naught M again, which is what we're moving. But M is the magnetic dipole moment per unit volume for this wafer. And in our scenario, this thin wafer has a small size, and of course that corresponds with very little current going around its edge, and the ratio of its height to diameter is very big. So M is just typically M is equal to IAB, which A and B are just the distance ratios, or like A and B. But these ratios are so off and I is so small that our M is just a very small number. So our field for this thin wafer is just very small. So what we're removing from our space of a large magnetic material is just B minus, well, the new field is just B, and the original field was B naught, of course. And what we're removing is just such a small amount of magnetic field that it's practically nothing. So B is just basically about the same as before. So B is equal to B naught for this problem. Now again, we're finding H in terms of H naught and M for this cavity. And of course, typically H is equal to 1 over mu naught B before this cavity. And with our cavity, it practically has no effect. So it's still just H is equal to 1 over mu naught B. So plugging that back in to find H with terms of H naught and B, we'll see that H is equal to, well, plugging back into H naught, our original given equation, H naught is equal to 1 over mu naught times B naught minus M. We'll see that this is still just H, so instead we get H naught is equal to H minus M, which when rearranged, H is equal to H naught plus M. So it's just the same as before, as this cavity has really no effect on our magnetic material. And those are the 3 solutions for this problem. I hope you understand it all. Please leave any comments below. Thank you.